We are carrying on from question 4, part C of the March 2018 paper 42 short answer question paper. We're looking now at a graph. We're told that chlamydia is a sexually transmitted infection, an STI, and figure 4.2 shows the number of reported cases of chlamydia in females in each age group in one country. So if we look at our graph, we've got the number of chlamydia cases in 2008. So we're just looking at a snapshot of 1 year. Then we've got age groups, 10 to 14, 15 to 19, all the way up to 65 plus. We can see we've got the scale going up here in 50,000s, and that's covering 1, 2, 3, 4, 5 blocks. So 50,000 divided by 5, it's 10,000. Your handwriting is horrific today. Per little block. Okay, so now what are they asking us? They are asking us to describe the results shown by the data in figure 4.2. Do you see there? It just says describe. It does not say describe and explain. It does not explain. It does not say justify. It just says describe. So we need to look at our graph and we need to say, okay, what do we see? Well, we see this massive jump going up between the 10 to 14 to the 15 to 19. And then we see a gradual decline. And then we see nothing above the age of 55. And that's all we're looking at, is just that description. So if we turn our scribbles into words, we have an increase, our overall pattern. Remember, we always start a description with an overall pattern, and that is an increase, then a decrease. Okay, so then we get a little bit of more details. So there is a large increase from how many cases in the 10 to 14? Well, we can see it's not quite on the line, and it's not on that line. So halfway between, two blockies would be a 5. So we have a 10 and a 5. So 15,000 cases in 10 to 14 year olds. So from that to how many have we got? Also between here again. So half a blocky under 350. So 350,000 minus 5,000. So to 345,000 cases in the 15 to 19 year olds. And what we've done there is we've described this specific increase, and we've also given data, which is always valuable when you're describing graphs. So who is the peak? Peaks are nice. So the highest number of cases is in that 15 to 19 year old age group. Then we have a gradual decline to 20 to 24. But you see how it goes gradual, then it goes steep, then it goes gradual again. So if we wanted to get into more detail here, we can work through that as well. We have to consider how much space we have here. So we've said that there is a decrease. We can say that there is a steep decrease between 20 to 24 years old and 25 to 29 years old. But we want to be really sure that we mention there's no cases in these two upper age groups. So there are no recorded cases for above age 55 years. So we filled our space nicely and thoroughly with very specific descriptions of the graph. So when you're asked to describe, you only describe. So D carries on with this story about chlamydia, tells us chlamydia is caused by a bacterium. So suggest a treatment for chlamydia. So what do we use to treat a bacterial disease? We use antibiotics. And then state the name of one other STI, just one. So if you give more, you're not following instructions. The instruction is one. So the other big one, of course, would be HIV, major STI that is included in your syllabus. So one that you are expected to be familiar with. Part 3. Complete the sentences about the spread of STIs. So you've got to read through the whole thing and you're going to think about what is going to fit in the gaps to make these sentences make sense. So STIs are transmitted through the transfer of something during sexual contact. One way individuals can avoid the spread of STIs is to use a type of something contraception. One example of this type of contraception is something. So STIs are transmitted through the transfer of bodily fluids. It has to be fluid transfer for this STI to transfer. One way individuals can avoid the spread of STIs is to use a type of what contraception? There's only one type of contraception that stops the exchange of bodily fluids, and that, of course, is your barrier contraceptive methods. So, to use a type of barrier contraception. One example of this type of contraception is a condom or a femidone. You've got the choice of both methods, but as long as it has to be a barrier method that you're giving an example of. And that total 14 marks. We reached the end of that question. So we move on to question 5. 2,4-D is a synthetic plant auxin that is used as a weed killer. Researchers investigated the effectiveness of different treatments of 2,4-D on the control of the weed Carniza canadensis in fields of maize, Zea mays. The results are shown in table 5.1. So you've got to be awake, you've got to be thinking. Because yes, they're talking about auxins, they're talking about weed killers, we're talking about control here, but this is an applied question. So we need to be familiar with what it is they're telling us. So we have treatments A through G. So different types of treatments. Okay, they're all using 2,4-D, but if we look at it, the difference is on the time of treatment. So A is only on day 7, B on day 23, C on day 33. Then see here in D, E, and F, they've got different arrangements of 2 treatments. And G, we go all the way up to 3 treatments. We've then got information on the mean dry mass of weeds, so grams per meter squared, so the biomass of the weeds. And then we've got the weed density, a number of weeds per meter squared. So this is the number of plants, and this is how effectively how big they are. So we could have a high density of tiny plants, or we could have a low density of big plants. So really, to understand how much weeds there is, we need to know both of these, both the dry mass and the density. And we can see that there's quite a big variation in terms of the effectiveness of these different treatments. So we can see that in the dry mass, we've got a high dry mass here on treatment A, going all the way down to F. Looks pretty good, 0.07, much less weeds than A. And the same thing on density. We see a high density also on A, and our lowest density we can see is on F. So it's looking like treatment F might be the way to go. And it's really important to take that time to really understand that data that you're looking at, so that you're understanding before you go and you tackle that question. So A, part 1. Maize farmers that had been using treatment C, so make a note of what treatment C is, were advised by the researchers to change to treatment F. Well, that doesn't come as much of a surprise because, of course, we've already seen that F looks to be the best option for these farmers. Discuss the advantages and disadvantages of changing to treatment F. So we can't just look at the positives, we can't just look at the negatives, we need to consider both. So set out and do it sort of systematically, okay? That you're going to use advantages of and then disadvantages of. Have a plan to answer this question. So if we consider the advantages, so the advantage is, sorry, 4 marks, we're going to aim for 2 of both, of treatment F, are that, and we already noted it, we've got a very low dry mass and density. It results in lower dry mass and lower density of weeds. Why is this important? Okay, why do we want less weeds? We want less weeds so that we have less competition with the crops and therefore we have higher yields. So this reduces competition between weeds and crops, increasing the crop yield. Great, fantastic. So it all looks brilliant, but there's a catch. What are the disadvantages of F? The disadvantages of treatment F are, now we've got to think of 2 things. If we look at them, so we've dealt with this last 2 columns. So what is this timing of treatment telling us? The timing of treatment is telling us that here in C, we only applied once, whereas in F, we need to apply twice. So we are using double the amount of weed killer. Double the amount of weed killer means double the time and double the price. It's more expensive. It also means double the environmental risk, because every time we use that weed killer, we have that potential impact on the surrounding environment and the naturally occurring plants. So, are the use of more treatments, more applications, sorry, which uses more time and costs more money. There is also an increased environmental risk. So we have advantages and we have disadvantages, and we've certainly covered 4 value points to get our 4 marks. Suggest then 2 factors that could decrease the effectiveness of 2,4-D. So we're using 2,4-D. What is it that could make the weeds not respond? Well, the big one, if they have resistance. So if the weeds are resistant, so resistance of weeds to 2,4-D. Perhaps it rains after you apply and then the weed killer is washed away or something like that. So there's a lot of different factors that you could suggest here. But the other one, that's a big one, of course, is that different plants are going to respond differently in the same way that our weeds and crops respond differently. So different types of weeds might also respond differently, and it's going to depend on what type of weeds the particular farmer is dealing with. So the type of weed could decrease the effectiveness if it is a weed that is potentially not as susceptible. Then it's going to have decreased effectiveness of 2,4-D. So linking on to that, okay, we just mentioned that crops and weeds are going to have different responses. Now they want us to explain how 2,4-D acts as a weed killer. And it says there, explain. So we've got to be specific, we've got to be technical. We've really got to explain how this happens. So what happens? The 2,4-D is absorbed by the plants, okay? But we've got to talk about here that why is it a weed killer, not a crop killer? It's absorbed by our weeds, not our crops, because our weeds have broad leaves. Remember, 2,4-D is a broadleaf killer. So 2,4-D is absorbed by broad-leaved weeds, but not by narrow-leaved crops. And they've told us that we're dealing with maize here. And maize is very much a narrow-leaved crop. Okay, what happens? 2,4-D, remember, they even reminded us, it's a synthetic plant auxin. Auxins are all about growth. So, the auxin in 2,4-D increases plant growth rate. But it doesn't increase photosynthesis, just growth. So the plant actually then can't photosynthesize fast enough to keep up with this growth. The plant can't photosynthesize fast enough to maintain the high growth rate. So if you're growing faster than you are producing food, eventually then you die. So this leads to death of the broad-leaved broad-leaved weeds. Okay, so that is how our 2,4-D is acting as a weed killer. So one last little bit before the end of this question. Auxin causes the shoots of a plant to grow away from gravity. State the name of this response. Well, we have 2 types of responses. We have phototrophic and we have gravitrophic. So responding to gravity, we would say that this one here is Gravitropism. Growing away from gravity is a gravitropic response. And we've reached the end of this question. So let's have a look at the next question and see how far we get. Because now we're moving into something completely different. We are moving towards digestion and we are going to have a look at some enzymes. So 6, part A, asks us to define the term chemical digestion. Not mechanical, chemical. Remember, mechanical is just breaking the food into small pieces. Chemical is breaking the molecules. So we're going from large insoluble molecules to small soluble molecules, which can then be absorbed. So the term chemical digestion is the breakdown of large insoluble molecules to small soluble molecules which can be absorbed. So now we've set up what we're doing. A student investigated the activity of the digestive enzyme pepsin. So pepsin, here we are now talking about digestion of protein. Figure 6.1 shows the apparatus used in the investigation. Test tube 1 had an egg white solution and pepsin. Test tube 2 had egg white solution, pepsin, and hydrochloric acid. Test tube 3 has got egg white solution, boiled pepsin, and hydrochloric acid. And test tube 4 has an egg white solution and hydrochloric acid. No pepsin. And then, of course, we have a stop clock. So it is important that you take the time to understand this. Yes, it's quite a practical question, but it is in our theory paper. So don't be deterred, don't be put off. Let's work through it still. So we're quite happy here. We've got protein and pepsin. We've got protein pepsin acid. And here we've got protein boiled pepsin acid. What happens when we boil pepsin? We have denatured the enzyme. So effectively, our enzymes in test tube 3 are broken. They're not going to work. Okay, so the appearance of the 4 test tubes was recorded at 0 and at 5 minutes. The protein in the egg white solution gives the solution a cloudy appearance. So the cloudy appearance clears when the protein in the egg white solution breaks down. So this is digested by pepsin. So where we've got pepsin working, we would expect that cloudiness to clear. Table 6.1 shows the results. So we have the test tube, what's in the contents, what it looks like at 0 minutes. They're all cloudy, they all started in the same place, and what they look like after 5 minutes. So test tube 1, cloudy to less cloudy. So here we had some enzyme action. Test tube 2, cloudy to clear. So this is looking good. This is digestion. Cloudy to cloudy, cloudy to cloudy. Test tubes 3 and 4, we had no digestion. And it makes sense because here we just have protein and pepsin. But remember, pepsin is a special one because it works at low pH. So here, excuse me, we have wrong pH. Here we have protein, pepsin, and hydrochloric acid. So here our enzyme is happy. Here we have the denatured enzyme that we talked about, and here we have no enzyme at all. just the acid. So acid is not digesting the egg white solution. So then we're happy with what's going on in this. And we run to the next question, which asks us to explain the results for test tubes 1, 2, and 3 in table 6.1. And because we took that time to really understand what's going on in those test tubes, this is now straightforward. So in test tube 1, there was some breakdown of protein. The pH is too high for optimal pepsin activity. In test tube 2, remember we're explaining, we're not describing. It went from cloudy to clear. We're explaining why it went from cloudy to clear. The enzyme activity is highest as hydrochloric acid causes a low pH. The low pH is optimal conditions for the pepsin. Then lastly, in test tube 3, that was the one, remember, that has boiled pepsin, denatured pepsin. The pepsin does not break down the protein because it was denatured. Use those technical terms by boiling. The enzyme is no longer functional because, for example, the active site is no longer complementary to the substrate. So we can't have that interaction between the enzyme and the substrate because the enzyme's been denatured. So again, a reiteration that they asked us to explain. So we are not describing the results. We are explaining the why the results did this. What was it in each of these test tubes that caused these results to happen? We'll carry on with the next pieces of this paper in the next lesson.